Welcome to the course of Fundamentals of Optical Fiber Technology. Before we start this course, let's try to understand why should we study this course. Fiber optics has transformed and still continues to transform the handling of information and telecommunications to the present day terabit communication links since the landmark discovery by Professor C.K. Kao in 1966, for which he got Nobel Prize in 2009. The fiber optics technology was invented, in fact, to answer the quest or to satisfy the quest of larger and larger share of the information. Nevertheless, at the same time, it also impacted greatly to another field which is termed as sensing. Today, you name any field, whether it is civil engineering applications or aerospace application, petrochemical, environmental, biochemical, civil engineering, any field you name where the fiber strands are not deployed. Emergence of specialty fiber afterwards has given further thrust to design and development of high capacity active and passive optical devices within the communication link. In my opinion, transforming the entire world into a small knowledge hub as well as realization of especially remote structural hand monitoring. Indeed, these two are the major advantages of the optical fiber technology. Let me just try to explain what do we mean by small knowledge hub. In the present age, if something happens at one corner of the globe, it immediately reaches, the information immediately reaches to another part of the globe and influences. That means we have the access of the information almost instantaneously. So, it is immediately where we are sitting, information can be reached to us at any part where we are sitting and any part the event is occurring. So, that way the entire world is termed as the global knowledge hub or village, I should say. Because of an ever growing demand of information and high capacity broadband communication link, complex and multifaceted application of optical fiber and the need for optical fiber based all optical ultra sensitive devices, indeed a wide area of application oriented research and development needs to be explored. To be shareholder of this high impact and technology to door research and development advancement, and we need to have deep understanding of the fundamentals and the salient features behind this technology, which is the key to highly accurate and sensitive application requirements. The motivation of this interdisciplinary course is to provide a deeper insight of the fundamental concepts and the principles, as well as the importance and wide spectrum of applications of fiber optics to the students from MSc, BTech, as well as research background. This course broadly will cover in different modules the following. First, introduction of communication theory and the importance of optical fiber communication. In the second module, we will discuss ray analysis of optical fiber. In the third, we shall discuss electromagnetic, that is modal analysis of the step index multimode optical fiber. And then graded index optical fiber will try to understand the basic characterization, the transportation characteristics of or guiding characteristic of graded index optical fiber. Afterwards, we will try to understand the loss mechanism. Is the optical fiber technology an ideal technology? For that, we will try to understand the loss mechanism in the optical fiber. We will also try to understand how the fibers are fabricated, which will be discussed in detail in experimental techniques in fiber optics. And then we will try to understand how the information is being propagated in optical fiber and the effect of optical fiber on the information. Of course, one part of that is already discussed, will be discussed in loss mechanism, but the second part, which is also very important, will be discussed in this part, which is pulse propagation, dispersion and chirping in single mode optical fiber. And before we end this course, we will try to understand various fiber based devices and its role in optical communication systems, and dispersion compensation mechanism which is employed in present days optical communication network, and finally nonlinear effects in fiber optics. Before we start the course, let us try to understand why we should, as I said, why we should study fiber optics. I just briefly gave you some kind of importance of this technology. As I said that the optical fiber was developed to answer the quest for higher and higher information to be shared with the people. Let's start with the beginning and try to understand some of the basic concepts of communication. Before we start the first module of this course, let's try to understand some of the basics of communication theory. Information needs to be shared, and which is very, very important for our survival. Being human, that is our advantage in terms of that we are good enough in sharing the information among ourselves. So when I'm talking about information, what is information and how it is shared? Let's try to understand. When I communicate, or when a speaker communicates to someone else, or a human being communicates to someone else, information is generated in the speaker's brain, and it is communicated to the vocal cord of the body. The information modulates the pressure, air pressure in the air column of our vocal cord in the body, and that pressure, modulated pressure, comes out from the mouth in terms of the pressure wave. So in this case, when I am speaking, my mouth is transmitter, and the person who is hearing me, his or her ear, is a receiver, and the medium between the two speakers is the channel which carries the information from transmitter to the receiver. So that is the basic concept of any communication system. We need to have a transmitter, we need to have a channel, and we need to have a receiver. So in this form, where a person is speaking and another person is hearing, is good enough to communicate when the distance between the speaker and the receiver is not very large. What happens if the speaker is far away, or if the listener is far away? Far away over a distance where even the speaker shouts, the receiver cannot get the information. So if the distance between transmitter and receiver increases, because the information is fed to the channel which is here open air medium, this medium scatters the information which is being propagated through it. For example, the pressure wave, it gets attenuated, and hence the distance over which the information can be transported in this mode of communication is very, very limited. We can communicate over a very short range. So if we have to speak, or if we have to share information over a long distance, what we use the term for that is telecommunication. Telecommunication comes from two words, the Greek tele, which means over a distance, and the Latin word communicare means sharing of the information. We are very, very familiar of this word tele in terms of telephone, which means sharing the voice channel over a distance, and television means sharing visual or images over a large distance. So if we talk about telephone or television, which is used to share the voice signal as well as the video signal, we require device, and in this case device is the handset of telephone or the television. So if we have to convey the information over a very large distance, we require some device. So this usual communication system now can be converted in the form of this one, where I will discuss these blocks. I will discuss these blocks and these blocks later on, but what you see here is this is the transmitter and this is the receiver. In this case, so what happens when I am speaking? The question is that I cannot communicate to a person who is very far away from me, and still the information is being created from my mouth in terms of the pressure wave. So this pressure wave has to be guided over a very large distance. So what we can do? So as I said that if we transmit this information in its raw form, that is pressure wave, it will carry some noise because there is some sound which will get accumulated along this original signal when it reaches to some receiver, and second thing, that the information will be degraded in terms of attenuation. So it is not wise for any communication system to transmit the information, that is the signal, as it is over a distance. So what happened? The signal which has to be transmitted, or the information which has to be transmitted, is not sent in its original form. another signal is used. So, the original signal which carries the information creates another signal, and this new signal, which is a transportation signal, is transported, or transmission signal, which is transported over a large distance. As an example, if what I am speaking has to be transmitted over a large distance, you know that what I require is a microphone. So, if you use a microphone, then the diaphragm of the microphone is a sensor, acoustic electrical signal. It converts acoustic wave to electrical wave. So, this electrical wave then cannot be sent into the open air medium. What we require is copper cable. So, in this case, when we switch from the open space guided medium, that is the speaker and the ear receiver, when the speaker is speaking and the information is being transported by open air medium, if I switch from there to electrical domain, where the information or the signal which is being transmitted is converted into another transmission signal, and that transmission signal is fed into a channel. In this case, that channel is not open medium, but in this case it is a guided medium, and hence this system is known as guided transmission system. So, the information is being fed over the wire and it is being received by the receiver. Receiver receives the information and decodes the information from the transmitted signal and filters out the original signal which is being sent or which is originally created by the speaker. Now, the question is another way to transmit. For example, this is good enough again for transmitting information over a large distance, but another way to design a communication system is the one here, where there is one antenna which acts as a transmitter and there is another antenna which acts as a receiver. And in that case, so what happens, the information which is being sent is again converted into another signal, the transmission signal, and which is fed to transmitter, which is in this case antenna. So, this information is being fed to the transmitter, and transmitter feeds this information to the channel, and in this case the channel is open air medium once again. So, this is another example of unguided transmission system, where the information is not guided in a given wire, and then the receiver, which is another antenna that receives information. So, what we understood from here is that for designing any communication system, we require a transmitter and a receiver and a channel. Another question from engineering point of view is that, as you understood from here, when we are talking about telecommunication, means information to be shared over a very large distance, we require a device, and device used to be very, very costly. For example, what you see here in this transparency, the antenna are not very cheap. So, when we are designing, and then there are lots of electronics also involved. As I said that in the previous one, we will discuss these blocks later on. So, there are a lot of electronics involved in this one, and that increases the cost. So, when we are designing a communication system, the question is that should we design a communication system that can carry one piece of information or one signal? So, of course, from the economical point of view, it is worth to design a system which can transmit not only one set of information, but huge, that is n number of information, where n to be very, very large. That means the channel, which is either a guided transmission channel or unguided transmission channel, should be capable of transporting not one information, but n number of information. Think of this in terms of a road. When you design a road, do you want to have a road which is very narrow, so that only one car can pass? No, of course. In today's generation, what we require is the highways, and that to 6 lane to 4 lane to 8 lane highways. Why? Because because there is a huge amount of traffic, and we want to have a smooth transaction of the traffic on the road. So, if you can think of the road as a communication channel for a communication system, and the car or the scooter or the bullock cart or the man who is walking on the road, or the boy or the girl walking on the road, all you can think of as information which is being transported over the channel. So, they said that it is worth to design a communication system which is capable of transporting not one piece of information, one set of signal, but huge amount of signal, and that is known as multiplexing. So, the question is that how the information is created, what is the information. See, in science and engineering, nothing can be understood without quantification. So, the question is, if I say information, how do we measure information? How do we quantify the information? So, we need to understand first how the information is created, how it is quantified, and then how it is dealt by the transmitter. Then next, how this transmitter feeds the information into the channel. Afterwards, the basic, I am narrating the basic questions, what we need to deal with. Then what is the impact of the channel itself on the information which is being transported by the channel from the transmitter to the receiver. Finally, how receiver processes the received information and filters out the original signal. So, these are the basic questions which we need to deal with when we need to design any communication system. So, let us first try to understand the information. When I am speaking, as I said that a pressure wave is being created. This pressure wave which is coming out from my mouth is exact replica of the pressure variation in my vocal cord. So, when I am speaking, what is varying? Time on the horizontal scale and the pressure on the vertical scale. So, if I plot the signal which is coming out from my mouth, it can be plotted in this fashion which is shown here. Because this signal, which is the pressure variation, varies with time and follows the pressure modulation in the vocal cord according to the signal which is generated in the brain. This is called analog signal, because it is analogous to the signal which is generated in the body. So, if we look into the signal, as I said that our objective is to quantify the information. So, here this signal is presented in the time domain, that is what we can access. Now, if I closely observe the signal, it is not a purely sinusoidal signal. That is, of course, you know all. So, but it is not a flat line. It is not a flat line. It has variations. It has variations like this. So, if I now try to analyze this analog signal, let us try to focus on a region where the pressure varies very slowly with time. Now, this is the signal which is being fed to the receiver, and receiver has to tune itself with the varying signal in the original signal. So, this is the region where the signal varies slowly, and if I look into only this part can be taken as, or can be considered as a part of this sinusoidal wave. Also, this sinusoidal wave is plotted in time domain. So, this is the region of lowest frequency in this original signal which is being created by the speaker. Now, at the same time, if I zoom into the certain other region where the pressure changes very fast with time, that means the receiver should be synchronized or should be good enough to sense that largest amount of variation or the steep variation of the pressure. So, if I look into this part can be considered as if the part of this sinusoidal signal, where of course, if you compare this signal and this signal, then the frequency of this signal is low and the frequency of this signal is high. So, that means any signal, what I am trying to emphasize here is that this signal has the lowest frequency component decided by this sinusoidal signal, and the largest frequency component which is manifested by this sinusoidal signal of high frequency. So, in general, any signal which is being transported used to have a range of frequency. See, the signal which is generated can be only measured in time domain. We are plotting, if I give you a task to visualize what pressure is coming out from my mouth, of course you will, because I am speaking and time is being collapsed. So you will be plotting the pressure variation with time. So we can best visualize the variation of the signal in time domain. But that signal in time domain has its own set of frequencies, as I am trying to explain here, the lowest frequency to the higher frequency. So the range of frequency content in any given signal is known as the signal bandwidth. In this case, F2 is the largest one and F1 is the smallest one. In general, in any given signal, the lowest frequency is very close to 0, and hence the bandwidth is taken as or measured as the highest frequency content in that information. So this is a very layman or very simple way to understand that the signal will be having a range of frequency content. But always it is not simple, and this method is not very accurate, because we are trying to zoom in into the region where the pressure varies very slowly with time, and we are trying to zoom in the region where the pressure is varying very fast with time. So yes, it gives me an estimation and the qualitative understanding, but not exact quantitative information. Yes, you can say that this is a quantitative information, but this F1 and this F2 are not very precise. So how to extract very precisely the bandwidth, that is the range of frequencies which are content in a given signal. So what we require to do is that we need to resort to some of the mathematical techniques, very powerful mathematical technique. So let's try to understand that. This is, as I said, is a signal bandwidth. So suppose I have now the signal which I have plotted here, V, is now, this is my any given signal. So now I have any signal which is being generated, which is given by Vt, and I assume that this signal is a periodic signal which is having a period of t naught. So from the basic information, we know that any signal, periodic signal, can be expanded in terms of orthogonal component, the cosine and the sine. So in this case, the signal is expanded as an infinite series of sines and the cosines. This is known as Fourier series for a given signal. So if you can see the left hand side, this is the signal which is in time domain, and if you see what is here, you have the signal which is in frequency domain. For example, 2 pi by t naught is the period, fundamental period of, or the period of this signal. Omega naught is known as the fundamental frequency of the signal. So as you can see, any signal given to us, periodic signal given to us, can be expanded in a series of orthogonal functions at a discrete frequencies. If I write this one 2 pi by t naught as omega naught, then you can see here is n omega naught t, and this is also n omega naught t. So any given signal in time domain can be expressed as a discrete sum of frequency component. So the right hand side exactly gives us the information about all the spectral content in a given time varying signal. In this case, A naught, which is the constant here, is defined mathematically by this integral, and it dictates the average value in the signal. The coefficients A n and the B n, which are the summation coefficients, can be obtained from this formula. These are the basic Fourier analysis which I am borrowing. I shall request you all to kindly please revise this Fourier analysis from any book which deals with this one at BSc level. So the amplitude coefficients of the spectral content here, A n, can be obtained in this fashion, and the amplitude coefficients for the spectral content omega naught in the sinusoid one, this is cosine one, and this is sinusoidal one, can be obtained from B naught. So in this fashion we can exactly determine. So what is required here? T naught is given to us. A naught in this series, A n and B n are not known. So A naught and A n and B n can be obtained in this fashion. That means any given signal which is periodic in nature can be exactly expressed or accurately expressed in infinite series of discrete frequency components. This can be this is called Fourier series, and I can simplify this expression of expressing this signal into a summation of orthogonal signal in this form. So, this is simplified version of this equation. V t is equal to C naught plus summation from n is equal to 1 to infinite C n cos 2 pi n t by t naught minus phi n. Here, so if I am expressing the same signal in this fashion or in this fashion, means the right hand side of the both signal must correspond to each other, and see the correspondence here. The C naught is same as A naught, which again gives you average power, average value of the voltage, the signal here V, and the C n is given by A n square plus B n square root, whereas the phi n, which is the phase content here, is defined by tangent inverse B n by A n. Now, this Fourier series, the Fourier expansion of the signal can, because here we are okay. So, the given signal can, as I said, the signal can be uniquely expressed in terms of the orthogonal signal cosines and sine. Sometimes it is easier to express the given signal not in terms of cosine and sine, but also in terms of exponentials. So, this is the first way to express the signal in terms of cosine. This is the simplified way, and here is another way in terms of the exponential. So, this signal is again expressed in terms of infinite series from minus infinity to plus infinity, with again a discrete spectral content which is manifested by n. 2 pi by t naught is once again the fundamental frequency, and rest are the overtones. Of course, in this case there will be two components, exponential component, for example, e to power I 2 pi t by t naught, and second will be e to power minus I 2 pi t by t naught. So, there are two, these are two phasors, if you are very good in understanding the phasor, which are moving in the opposite direction, but are oscillating at the same frequency, which is omega naught. So, this is nothing, it is not changing anything. Physically, it is giving the same information, that you have a frequency component at omega naught. And when these two phasors is e to power I 2 pi t by t naught and e to power minus I 2 pi small t by t naught are added up, it gives you the real component, which is cosine or sine. So, in this case, when we express the given signal in terms of exponential, the various coefficients V n can be calculated from this integral. V n usually the V n are the amplitude of the spectral content. This is my spectral content. So, V n are the amplitude of these spectral contents. In general, V n used to be complex, and as you can see from here, V n is, this relation gives you, this relates V n, the positive components to the negative components, that is V 1 to V minus, and these two are complex conjugate of each other. Of course, I need to relate V to C, and if you can see once again, V naught corresponds to C naught, but V naught and C naught are same, and that way they are also same to A naught. However, the coefficients here are related to coefficients here in this fashion. V n is equal to C n by 2 e to the power minus I phi n. So, what you see here, the coefficients here are complex, and so if we had to represent, because this is a series which has discrete frequencies, and so if I had to visualize this one, I had to plot on the x axis the frequencies, and because I have only certain discrete frequencies, I need to plot the amplitude here, but these amplitudes are complex in general. But so, if the amplitudes are complex, we require two kind of scales. One is the phase scale and another is the linear scale. Nevertheless, in many of the cases, this coefficient, though complex, used to be either pure real or pure imaginary. So, if it is pure real or pure imaginary, then we need to have only one scale where we can plot the spectral content in terms of arrows, each arrow carrying the amplitude at that spectral content. Let us try to understand. So, this is the plot of the spectral content when I express this signal in this fashion in terms of C. So, what you see here on the y axis, CNs are plotted, And so what we have here is discrete frequency. This is the fundamental frequency f naught, then the second tone, third tone, fourth tone, and like this. And the arrow which you see here is Cn, the amplitude at that frequency. Now, what is the impact if we change ourselves from this representation to this representation? As I said, this representation adds two components for the same frequency, e to the power I omega t and e to the power minus I omega t. That means if I shift from this expression to this expression, the representation will be double, as you can see from here. Nevertheless, if you see here, if I take the magnitude of Vn and relate to the magnitude of Cn, of course, e to the power minus I phi n will become 1. So, the amplitude at the spectral content omega in this expression is half of the amplitude at the same spectral content in this form of expression of the signal in Fourier series. As you can see from here, the red color one are the amplitude of the spectral content when we express the given signal in this fashion. And what you see here, the black arrows are the signal which is represented when it is expressed in Fourier series in form of exponential. So, what you see here, we have now two components at same frequency, that is f naught and minus f naught, 2 f naught and minus 2 f naught. At the same time, amplitude also diminishes to half of the value. Now, let us take an example. This is a function, as you can see here. The function is plotted. This is a very important example. Why I am giving this example, I will explain this later on. So, this signal is plotted in time domain. X-axis represents the signal, and this is again a periodic signal. As you can see, you have a square wave here, and these two square waves appear at a constant time interval, which is t, capital T here. And what you see on the y-axis is the function which is plotted. So, this is an example of periodic function with a period t, and it can be mathematically expressed because the amplitude is given here is a. So, amplitude could be either a or could be 0. So, if I look into, this is my 0 at this point. So, this is the width of this signal here is delta given. So, the value of this function is a if I take the value from minus infinity at this point to minus delta by 2 to here plus delta by 2, which is expressed in here. And then if I take the value of this function from this point to this point, that is plus that is t minus delta by 2 and minus delta by 2, then it is 0. So, this function which is known as gate function can be expressed mathematically in this form. So, now the question is that if I see this function, I will not be able to understand what are the frequency content in this one. So, how to find the frequency content in this case? Please understand this method which I discussed here, this one cannot be used in this case to find the spectral content, that is the lowest frequency component and the highest frequency component when the signal varies with time in the form which is depicted here. So, now how to understand or how to get exact amount of the frequencies which are content in the signal. Of course, because this is a periodic function, we need to express this function in orthogonal sinusoid or in terms of exponentials. That is what we have expressed here. So, this is in this case I need to get the values of Vn. We need to determine the coefficient Vn. If we know the coefficients Vn exactly, then the Ft is known in spectral domain. So, as we have already discussed that the coefficients in this expansion, when we express this function in a Fourier series where we are using exponentials, the coefficient is given this fashion. So, if I substitute now the actually here it should be a should be Ft. So, I have just substituted, for example, if you go here the Vn, here is the Vt. So, Vt is substituted in this case, Vt goes to Ft, which is a here. So, this is the after substitution, this is my integral, and this integral can be solved. If you solve this integral, you get this function a delta by t sin n omega naught delta by 2 divided by n omega naught delta by 2, and this is a very special function. It's like sin x by x. So, if I try to give you a feel of this function, which is known as sinc function, it is like this. This cannot be plotted properly here. So, this is the one which is the periodic function. So, this is a very important function known as sinc function, and as I said that it varies in a fashion which I have just depicted right now. So, this expression can be written in this compact form in this fashion, where the sinc function, this entire function is written as SA sinc, which is sin x by x, and this part remains the same as what you see here. In this case, what we have done, omega naught is now converted into the time domain. So, now we have this signal, now we can express this, we can write the signal in the exact form in the frequency domain using these Vn's. So, that is what expression will come out to be. This function is now expressed in this fashion in the frequency domain. So, if I look into this frequency, this expression, this Fourier series, the Fourier expansion of the function, it has this amplitude, which is A into delta. Delta is the width of one of this square wave, and then the t is a period. So, this is the amplitude, and these are the sinusoidal terms. So, if I plot, let us try to plot this one. As I said once again that these are discrete sets of the spectrum. So, that is why this expansion of a given function in Fourier series is known as discrete representation of the function which is periodic in frequency domain. So, let us assume that as an example delta is 1 by 20, t is 1 by 4, t is the time period. Of course, you should express that in second. Whenever I am not giving the unit, please add the unit. So, t is 1 by 4, which is 0.25. So, in that case, with this value of delta and t, delta by t comes out to be 1 by 5. So, this is how this signal will appear in frequency domain. What you see here, the envelope is the sinc function sin x by x, as I already explained, and these vertical lines which you see, which appears at discrete frequencies, represents the spectral content of the signal for these values. As you can see here, the signal appears at discrete sets of frequencies. That is why this way of expressing the function in orthogonal function is known as discretization of the given signal. Now, if I change the time, if I increase the time from t is equal to 1 by 4 to 1 by 2, then in that case delta t by t goes to 1 by 10 in comparison to 1 by 5. This delta by t here defines the amplitude. So, amplitude in this case diminishes when the time period increases. So, if I plot the same function here, which is expressed in this fashion for this value, then it will look like this one. As you can see, the envelope remains the same. It remains a sinc function, sin x by x. However, in this case, the amplitude goes to half, a by 5 to a by 10, and also additional frequency component. In the previous case, when t was 1 by 4, the frequencies were appearing at 8 pi, and now we have additional components exactly in between of 8 pi to say, so that is every interval of 4 pi in this case. That is, when we increase the time interval from 1 by 4 to 1 by t, amplitude decreases and the range of frequency component increases in the signal. If I further increase the time from t is equal to 1 by 2 to t is equal to 1, then as you can see once again the amplitude will go to delta by t, which will go to 1 by 20. That is, if you compare from 1 by 5 to 1 by 20, the amplitude has greatly reduced, as you can see here in the green curve. So, the amplitude reduces, the waveform, the envelope remains the same, and the vertical lines which gives you the information about the spectral content in the signal now gets densified. So, as the time period increases, more and more frequency components are required to build the signal. So, let us try to understand the impact of making t, that is a period, to infinity. If I make this period t infinity, that means these two are going far apart. These two, this one and these two blocks are going far apart from each other. That is, virtually we are left with only this block. Okay? So, this is called the gate function. What we had the previous one, like this one, is the square wave. So, in the limit t goes to infinity, we have left with only this block. And let us try to understand what will happen in this case. As I explained from this part, as t is increasing, the amplitude diminishes, the envelope remains the same, the shape of the envelope does not change, and the spectral content increases. So, let us summarize this point here. As t goes to infinity, the fundamental frequency omega naught decreases, because you can see the expression here, omega naught is equal to 2 pi by t. So, as t increases, the fundamental frequency decreases, and hence you have more compact frequency component sitting into the same envelope. Amplitude diminishes to a smaller value, but shape of the frequency spectrum remains unaltered. So, what we had in the previous case, we had the frequency component at these two distances. Now, when we increase the time interval, then this distance decreases. We have more components sitting in between this, we have one more component here. If you further increase the time period, then again another component appears over here. As we keep on increasing the time period, we are bringing the frequency closer, 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 closer. That means at certain point of time, the idea of having discrete frequency component in a given signal will no longer remain valid, because the frequency will be so tightly packed and close to each other that it will appear as if a continuum. And that is what is termed as Fourier transformation. When in the limit t goes to infinity, then this signal can no longer remain a summation or over the discrete numbers. It goes to an integration. So, this is the Fourier transform. If a function is known, it can be expressed in this fashion, that is in frequency content, or if a function is known, I can get the frequency content of this function by solving this integral. Similarly, if a function is known in frequency domain, for example, I can extract the information in the time domain by this integral. So, if this is the Fourier integral, this is known as inverse Fourier integral or inverse Fourier transform. So, there are two ways. If I know the signal in time domain, I can extract the information of the signal in frequency domain. If I know the signal information in frequency domain, I can extract the information in time domain. Let us try to have some example here. So, this is left hand side, what you see is the function in time domain, and what you see in the right hand side is the Fourier transform. So, as you can see, this is a gate function and its Fourier transform is shown in right hand side in this form. Now, here the function is known in time domain and I am trying to get the information in frequency domain. Now, if I know this function, can I get this information? As I told you previously, with a mathematical tool, yes, it is possible. If I know this one, information in frequency domain, I can do the inverse Fourier transform and get the information or can convert this into the time domain. So, it is a vice versa, it is reciprocal to each other. Similarly, this is very important one. In this case, the function in time domain is a spike, what we call a Dirac delta function or a pulse, impulse I should say. So, if I have this function in time domain, then its Fourier transform is shown in this fashion. What is happening here? As you can see in the previous example, here, if I make t, if t is extended to infinity, at the same time this delta goes to 0. If delta goes to 0, please see here, this entire, then this will be not very simple. So, this delta goes to 0, in the limit that delta goes to 0, how can we get this spike? By making this t infinity and reducing this delta to the width of 1 square. So, that is called a Dirac delta function and its Fourier transform is shown in this fashion. That means, if in time domain, if I have an impulse, in frequency domain it extends from minus infinity to plus infinity, means you have a continuous range of frequency extending from minus infinity to plus infinity. If I know this function, can I get this information? As I said, yes. So, if I have a function which extends in time from minus infinity to plus infinity, to know its spectral content, I have to use Fourier transform as inverse Fourier transform in this case, and that will give me the information in frequency domain. So, a function which expands in time domain from minus infinity to plus infinity has only a single frequency component in frequency domain. Another very important example is a function in the time domain which is sinusoidal. So, this is the function which extends from minus infinity to plus infinity. If I do the Fourier transform of this one, this is the Fourier transform That is, I have only single frequency in this case is omega naught. And here let me try to make you understand this sine wave is function is f t is equal to cos omega t, which is this function is extending from minus infinity to plus infinity. It is infinitely extended function in time domain, and its frequency component has only one frequency in the Fourier transform, which is omega naught. So let's summarize. If I have a function here whose Fourier transform has to be obtained, and if I know the Fourier transform of that function as capital F, then if I express this function in time domain, then and if I try to find its Fourier transform, it will be small f again. Means if the Fourier transform of small f is capital F, then the Fourier transform of capital F will be small f, and that is called the symmetry property of Fourier transform. As an example, if the Fourier transform of this spike is this function, then if I take a function in time domain which is analogous to this one, its frequency transformation or frequency content will be analogous to this one in frequency domain. This is what here. This is in frequency domain. I converted I have opted a signal, similar signal in time domain, and if you see the Fourier transform of this one, it is exactly this one here. Now, the scaling property of the Fourier transform, which is very, very important. Suppose I have a function time in time, which is f t, and its Fourier transform is f omega. Now, if I rescale the function, that is, if I multiply f by at, the time in at, if this a is a rescaling parameter here, then the Fourier transform of this one is defined by in this fashion f omega divided by 1 over mod of a. So, let us try to understand the impact of this one. If a is very, very small, that means I am trying to narrow down the function in time domain. So, if a is very, very small, then 1 upon a will be very, very large. So, if a function is contracted in time domain, it will expand in frequency domain and vice versa. So, this is the one. I had this function and here it was delta, the information given to you. So, this is the width of the function in time domain, which was delta. Now, if I multiply this delta by a number so that it gets reduced in the spike, then you see here the function in frequency domain extends from minus infinity to plus infinity. So, with this I like to end the lecture here, and the next lecture we will try to understand how the information is discretized and quantified. Thank you.